All right, folks, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 318, Electronic Circuit 1. And today is essentially the very last lecture for this semester, 26. And in 2 days, we will have very last exam, and that'll be all. And today, I think I prepared three more examples for us to do exercise together, and very likely to occupy the full lecture. But in the middle, anytime, if you have any questions regarding the exam and or say any aspects of the exam or this course, just bring it up. Okay, so very last lecture. Hopefully we can receive as much as possible information helpful. Okay. All right, let's get started. Okay. Nothing special, nothing new. Directly, just an example number 5. And given circuit, some parameters, necessary parameters, and find DC circuit and analysis equations, and AC circuit and corresponding small signal analysis equations. Okay. And here is telling you, including the output resistance or not. Okay. You got to be careful on this. This information obviously is very important. Okay. The problem can tell you either include or not, or let you know by giving you the VA, right? The VA information. So let's go ahead. Okay, I will present the solution on the paper, step by step under DocCam, but let's do the DC circuit and the DC analysis first. Equations only. Okay, give you guys 5 to 10 minutes, maybe 6 minutes. Okay. 6 minutes to do the circuit, and equations should be more than enough. Go ahead. After 6 minutes, I will present the solution under the DocCam. Okay. Once again, any questions, bring it up right away. Okay. Go ahead. So I'm here presenting the DC circuit, which should be easiest part. And what we have here are 2 resistors. In the middle, we have IB coming out. And it's also actually very helpful for you to understand, even to label the terminal, collector, emitter, and the base. And therefore, you are realizing that this is NPN, right? And NPN. And also, actually, this is due to the location of the output at the collector is actually common emitter circuit, right? This is a DC circuit. If in the exam it is asked, you need to answer the type of the transistor, you need to answer the configuration, and etc. So this is circuit. I think this is fine. You're open all of the capacitors. Right? We are seeing 3. So what DC equations we have? First of all, very regular. So first of all, you want to do a KCL at base. Right? You want to do a KCL at base. So if you're assuming the current direction like these, so obviously this guy is the IB. This is the guy is the IB. So 15 minus VB divided by 5K equals to IB plus VB minus 0 divided by 10K, right? So the first KCL at the base. KCL at the base. Right? Second, quite regular, is the VBE loop KVL. VBE loop KVL. Right? You realize that is down here, right? Inside of this loop. Inside of this loop, you can have VB just equals to VBE plus 100 times IE, right? And this equation is nothing but VB equals to 0.7, which is given, plus 100 times. You got to be careful because in the first equation, what you have is IB, right? IB and VB, 2 unknowns, right? In the second equation, you try to not to introduce more unknowns. So you keep VB and rewrite IE in terms of IB, right? Of course, this is pretty much an extra equation. IE equals to 1 times beta times IB. And the last one is the top to bottom KVL, which is 15 just equals to 1K IC plus VCE plus 100 IE. Therefore, they equals to 1K times beta IB plus VCE plus 101 plus beta IB, right? So eventually, what you have is 3 unknowns. 3 unknowns. What are those 3? VB, IB, and VCE. Okay, VB, IB, and then VCE. Okay. If the problem asks for anything, you can find them by this, right? You can find these 3 guys. And from IB, you can find IC, okay, which really matters. And from VCE, you can check the active region, right? And this is DC. This is pretty much the DC. Take a look to see any questions. I think based on performance of the homework, I think you guys are fine. Okay, homework 5 is all about the DC analysis of the BJT. Okay. There's some small tiny things you need to be careful. Other than that, I see no problem. No problem. Also, if you have any questions regarding the homework 5, just bring it up today as well. Okay. So, any questions regarding this DC analysis? Any trouble? Any concern? All right. If that's fine, then go ahead. Another 5 minutes to have the small signal circuit and small signal analysis equations. Go ahead. Another 5 to I'll give you another 6 minutes. Go ahead. All right, let's take a look at the AC here. Okay, so the AC circuit is basically, we begin with the small signal model of the transistor itself. Everything labeled here. And then we find the base. That's connecting to R1 and R2 parallel. Okay, 5K and 10K parallel, and also connect to a 500 ohm. And then is the V source. The collector is what? Collector is, first of all, it's connect to a what? 1K, right? And also its output. And of course, don't forget we have a output resistor between the collector and emitter, or not, over here. And then the last emitter. Emitter is what? Ground. Does that make sense? So what do you see? R0 and 1K parallel. Okay. So due to this, the output equation V0 is just equals to negative GM V pi times R0 parallel to 1K. This is one regular equation. What else we can have? Input and here, trying to establish relation between the V pi and Vs. What is it? What is it?
A voltage divider.
We can do a voltage divider. Okay, we can do a voltage divider here. Okay, due to here, there's no resistor. So therefore, the input and as two mentioned, so V pi is equals to what? V pi is the voltage across R pi as well as 5K parallel was 10K, right? So V pi equals to Vs times the voltage divider. In the numerator is 3 thing parallel, right? Denominator is this 3 thing parallel plus 500. Does it make sense? This is the input end. So if you count, we have V0, V pi, and Vs. Three unknowns, but 2 equations. Enough to find the gain V0 over Vs. Take a look to see any questions. This is a fairly easy problem, but any questions, any concerns? As a warm up for today, obviously.
It would be all right if we did a KCL there as well, correct?
Absolutely. And if you do a KCL, which means here alternative equation, right? Alternative KCL at the base. Is that what you mean?
Yep.
All right. So we can assume the current like flowing here, because the current here is obviously flowing towards right. Okay, due to the polarity of the V pi, right? And current here go downwards. So the KCL gonna be Vs minus V what? What is the voltage here?
V pi.
V exactly, V pi. Okay, V pi Vs minus V pi divided by 500. This equals to V pi over R pi plus V pi over 5K parallel was 10K. I don't know if this makes sense, but this is exactly same equation, okay, as the second one. Okay, absolutely exactly same. Okay, exactly same. Okay, so the red color is alternative equation to the second input equation. Okay, voltage divider. Okay. But be careful, why we are able to apply the voltage divider. because the emitter is directly the ground. So you can consider this part is basically isolated. Well, not isolated, of course, but what I mean is this is an independent loop. The voltage divider works. If you have RE here, obviously you can't do the voltage divider. However, KCL at the base remain working. Okay, always remember what I said. Okay, and has been said through the entire semester. KCL, KVL have no constraints. Voltage and current dividers do. Okay. Good. Any other questions? Any other concerns? If this is fine, then we can speed up a little bit. For next example 6. Go ahead. Give you 10 minutes to do both DC and AC. Still the same. Okay, find a circuit and find the equations. Okay, the circuit and equations. No calculation. Okay, nothing. So go ahead. 10 minutes to do everything. Okay, to do everything. All right, let's see the solution here. So the DC circuit is fairly easy, like this, right? And we open C1, and then we end up with this DC circuit, and quite regular. We are having a KCL at base, and then what we have is this. And of course, here you see CBE. So you know this is a NPN again. NPN. And because of the input and output location, this is common what?
Collector?
Collector, correct. A common collector, which is also called emitter follower. Emitter follower. So the KCL at its base then actually is 5 minus VB divided by 200K equals to IB plus VB minus 0 divided by 120K. This is not something difficult. And then in the VBE loop KVL, which is down here, we have VB just equals to 0.7 plus 1 plus beta IB times 4.5K, right? From which we can find IB and VB, right? And top to bottom, KVL is 5 equals to VCE plus 1 plus beta IB times 4.5K. Right. This is where we can find the VCE. Right. Once again, from IB you can find IC. And that's what we need for AC small signal analysis. This is DC part. Any questions? All right, if not, another I think this time 5 minutes is more than enough. I could give you 3 to 5 minutes to finish the AC part. And of course, we didn't do this in previous example, but at the beginning of the AC, what you need to do is calculate what? R pi, right? Calculate R pi. And also maybe you need R naught, depending on the problem, right? Depending on the problem. And in this particular problem is telling you neglecting the output resistance, so you don't need it. In previous example, you do. Okay. You still need to calculate the R pi and the GM. Both equations are available from the one of our handouts, the slides. You should print out, right? Anyways, go ahead for the AC for another 3 to 5 minutes. All right, let's see the small signal circuit. Okay. Once again, we place the basic model right in the middle. And earlier we have identified this as NPN. So we are applying NPN model. This is very important because if it is a PNP, you will have different circuit. So this is basic model, and then we're extending the circuit terminal by terminal. So base is once again quite regular. Is connect to 200 and 120K parallel, shooting to the ground here, and also base connect to 1 kilo ohm, and then series connected with the source. VI, okay, here. Sometimes the source is named as VS, sometimes VI, but doesn't matter. You understand the AC source here is the one in the denominator when we try to find the gain, right? Okay, this is the base. Next is the collector. Collector is fairly easy. Collector, what do you see? Collector has nothing resistor, okay? Just directly shoot to what? The ground. Collector directly shoot to the ground. Okay. The next, the emitter. Emitter, first of all, is the output. Okay, you need to understand. First of all, emitter is output, and then emitter also has a resistor R4. Okay. R4, which is 4.5 kilo ohm, and then shoot to the ground. Feel free to use this version of the circuit. However, once again, I do a conversion to make it better look by dragging this out, or say dragging this emitter to the top. Now drag this emitter to the top. Okay. So I end up with this. Input and look the same. Okay. Input and not much difference. But I'm dragging the emitter out up and then make the R pi lay down horizontally. In the meantime, realizing this is the base, and here is the emitter. V pi in the middle. And therefore, the resulted dependent current source like this. Because one end of the dependent source here, collector, is what? Ground. So I place it on the bottom. And therefore, the current direction of the dependent source is what? Upward. Meantime, emitter has a resistor 4.5 kilo ohm between the emitter and the ground. And emitter is the output. That's it. This is the circuit. Obviously, better look. Easier to write equations, right? And based on which I'm starting to write equations. And in this, I'm seeing 3 meshes. However, I still prefer the KCL. So one KCL at the base. And I believe another KCL at emitter also going to be helpful. At the base, what is the current equation? So VI minus VB divided by 1K. This current equals to VB minus 0 divided by 200K, parallel with 120K, plus the current here, right? The current here is what? How do we express this current? How about V pi divided by R pi? It's Ohm's law. This is the current here. Then the emitter PCL, we have V pi over R pi, which is this current, equals to current here, and then plus the current here. I mean, plus the current here, obviously, GM V pi equals to current here. Current here is what? Current here is nothing but V naught over 4.5 K divided by, right, V naught divided by 4.5 K. Doesn't make sense. 2 KCLs. Be very careful here. If you're writing an output equation here, V naught equals to 4.5 kilo times GM V pi. Is it right or wrong? This one, output equation here.
That's wrong.
It's absolutely wrong. Okay, why is it wrong?
Because you also have the V pi over R pi current flowing in.
Yes, that's basically right. Or you can explain like the VGM V pi current here is not completely goes through the 4.5, right? This is the circuit 1 knowledge. So your current here, reach here, is split 2 branches, right? So this simple output equation from this circuit, no, it's not right. Okay, it's not right. It's not right. And then we can count how many unknowns. 1, 2, 3, 4. 4 unknowns. 2 equations. Of course, we need one more. What equation we can have?
You need to write one for VB.
Yep, we need to write one for VB, which is
V pi plus VO.
V pi plus V naught. V pi plus V naught equals to VB. Okay, no problem. This is correct. This is correct. How we interpret this? There's more than one way to interpret it, but My way is voltage at base minus voltage at emitter, which is V naught, equals to voltage potential between these two, VBE, which is V pi. VB minus V naught equals to V pi. It's my way to explain it. Or you can have another way to explain this as what? KVL. You have a KVL inside of this loop. You have VB here, V pi here, and V naught here. 3 voltage inside of this loop. Okay. So if you write a KVL inside of this loop, same equation. Different way to explain. Different way to think. Now we have 4 unknowns, 3 equations, done. Any questions? Anything, anywhere we want to discuss more? All right, if this is fine, then we go ahead for the very last example. This is actually not analysis. They're just go ahead to find the DC and AC circuits. Okay, just the DC and AC circuits. Right? Involve everything. Okay? Output resistance needed. And also you need to clearly label the transistor terminals and the small signal parameters. If you recall the previous exam 2, you need to realize to this problem, you need to differentiate Q1 and Q2 by giving different subscripts. Okay, remember that. You label GM V pi and the GM V pi, they are not same GM V pi. You're labeling the base emitter and the collector for Q1 as BCE. They're not the same BCE for Q2. Okay, you need to apply subscript to differentiate them. Remember that in midterm 2? All right, give you 5 minutes to do this problem. I will present the solution at around 2 o'clock. All right, let's see the solution here. Well, the DC circuit is fairly easy as this, right? So I'm beginning with VCC all the way down to the ground, and along this path we have R2, R3, and R4. And then we have R5 here. And then between R2 and R3, we have a base of Q2. Between R3 and R4, we have base of Q1. Right? And between emitter of Q2 and the collector of Q1, you have resistor R6. And then you have R7 as the emitter resistor for Q1. This is DC circuit. So basically, by counting how many resistors you have from the original given circuit, you can also check your DC circuit or an AC circuit. given is up to R7, right? And due to the open of the C1, R1 is useless. R1 becomes useless, right? R1 becomes useless because one end of R1 is open circuit, right? Open circuit means no current through R1. No current through R1 means no voltage across it either. So it's gone. The R1 is gone. It's useless. Okay. So this is the only 6 resistance left. DC circuit. To AC circuit, what do we have? Once again, okay, we begin with 2 small signal model. And obviously we need to realize both Q1 and Q2 are NPN, right? NPN. So the current direction downwards. GM1, V pi 1. Does it make sense? B1, C1, E1. Definitely makes sense to you. But GM1, V pi 1. Okay, you need subscripts as well. So this is V pi 1, right? And this is R pi 1. This is Q1. Now we are done with Q1. Well, no, not done yet until we involve the R0 one, right? Problem asking for involving the output resistance R1, R0. Okay? So this is the Q1. This is Q1. You can plot the Q2 above it or on the same horizontal line. That's okay. Either way, okay. Because you notice that the Q2's emitter is connecting the collector of the Q1 through R6, right? This is something you observed. So what we can do is make the emitter of the Q2 at the same level of C1. Once again, you know C1 connect to the emitter of Q2, E2, like this. So based on this, we can do the small signal model for Q2. And in this small signal model, we have everything with subscript of number 2, right? Two small signals are placed right in the middle of the paper. And then we start to extending the circuit terminal by terminal. Let's begin with the base 1, B1. So B1 is connecting what? R4, R3, and the source, VS, right? So B1 is, first of all, connect to R4. And also be very careful, R3 and R4 are not parallel this time. Does it make sense? That's very important, okay? You need to realize that R3 and R4 are not parallel. Okay? R4 is between base 1 and the ground. R3 is between the base 1 and the base 2. Base 2 is here, okay? So you can have R3 here, and then connect to base 2 like this. Makes sense. R3, R2, done. The further base 1 connect to the source, okay. Or say the base 1 connect to the positive polarity of the source, and the negative polarity of the source is the ground. Now let's take care of the next emitter one. Okay. Q1's emitter. Q1's emitter is connected to R7. The other end of the R7 is the ground. Okay. This is fairly easy, right? This is the emitter line. Nothing else. The last, let's take care of the collector of C1, and we notice that C1 has been taken care of. It's connecting to E2 with R6 in the middle. Okay. So Q1 is done. Basically, Q1 is done. Next is Q2, and in Q2, let's begin with B2, the base of the Q2. By observing the given circuit here, the B2 connect to R2, R3, and R1, right? R3 is the resistor between the B2 and the B1, and then we still need to take care of the R1 and R2, right? So first of all, R1 and R2. What is the relationship between R1 and R2? Anyone tell?
They're parallel.
Very good. Okay. The parallel between base 2 and where?
Ground.
Ground. Okay, so R1 parallel was R2, and then to the ground. Now here by this, you know what I mean, right? It's not the intersecting point. It's not connecting. It's just opposite. This is a base 2. Once again, R1 and R2 are parallel. Okay. So R1 is between the base 2 and the ground. R2 is between the base 2 and the ground as well, right? That's why these two are parallel. Base 2 done. And the next, the emitter 2. Emitter 2, we notice that we have taken care of it. Emitter 2 is just a connect to R6. That's it. Nothing else. The last one is the collector 2, right? The collector 2, first of all, is output. Okay, never forget this. Collector 2 is output, right? And also collector 2 connect to R5, and the other end of the R5 is ground, right? And then we are done. And then we are done. So take a look, because I remember in midterm 2, this problem in midterm 2 was not as good as I thought it should be. So you need to improve this time, maybe. Differentiate 2 transistors by different subscript number. Okay. And other than that, the entire procedure is presented. Any questions? Take a look. Let's see any questions you have. Any questions from you guys about homework 5? For example, this problem here. With this problem here. The key is, what is the current through the 10 kilo? What's the current through the 10 kilo?
IE.
It's not absolutely not IC. Okay, the location is the collector end. However, it's not IC. It's IE. Okay, but of course, if you directly say IE is actually confusing. You need to understand how is it IE. Okay, the reason is a KCL at collector. The KCL at this collector here. Okay. First of all, where is IC? Here is IC. Okay, everybody, you need to understand here is IC. And here is what? IB, right? So if you have a KCL at this node, you got IC plus IB equals to the current flow through 10 kilo ohm. IC plus IB equals to IE. That's why IE is correct answer. Okay, this is the thing. Similar thing here. What's the current flow through 8K? Down here. What's the current through the 8K here? Of course, by grading here, you know, IC is wrong. This is not absolutely not IC for the same reason. Because IC is here. IB is here. 1 KCL at this collector here. You got IE, which is equals to IC plus IB going through the 8 kilo ohm. Okay. So be careful. It's not the location, but the it's at a collector and so it's IC. No. We're not relying on the look. We're not relying on the memory. We're relying on the reality, okay, the fact. This is the homework 5. Homework 6. What is the homework 6 actually? See. Well, one thing here I want to bring up, regardless the questions about it from Noah, the textbook solution available is actually using what? Can anyone tell how they solve these DC analysis here? It is using RTH and VTH. What are they? Anyone knows what are they?
Teflon drill.
Say that again.
They use Teflon drill.
Yes, it's 7ing. They're using 7ing theorem. They're using 7ing theorem, which is correct. However, if you understand it, you feel free to use it. Okay, because I don't like any 7ing Norton voltage divider, current divider, but they all have constraints. Only KCL, KVL are what? So all pass. Okay, all pass. Okay, all pass. It's you can use it for any circuit, any scenario. Okay. Even in power electronic circuit analysis, which is completely nonlinear, KCL, KVL remain valid. They remain working. In future courses, you're probably going to realize that. Any other questions? Any other concerns regarding the exam?
I have a really quick one about the project.
A project. Okay, go ahead.
When you take the common emitter circuits and you simulate them with the load, do you attach a capacitor as well, or do you just have that resistor?
You can actually do both. You can therefore observe the result. And because you attach the capacitor and then you will have less or even 0 DC in the output. And if you don't attach the capacitor, you probably see a significant offset by DC. But I'm trying to observe the gain, basically concentrating on the AC gain. With resistor and without resistor 10 ohm, you will see a huge difference between two gains. And that's my point. As long as you are achieving that, then that's indicating you are doing the right thing.
Okay, so as long as we're demonstrating that the gain changes significantly by
Yep.
adding that
Yep.
resistor, it's good. Okay.
Yeah. And as
Thank you.
to how much the gain is supposed to be, well, of course, there's no uniform answer for that. It's a uniform key, no. But with the, say, your first CE, after the design everything here, and you attach to the 10 ohm load, you try to see that's the V naught and the VI, and then you do a division. The gain should be very, very small, at 0.00 something. It should be very small. The reason is, as I said, your load is very small. Your output impedance here is too big comparing to this 10 ohm load. That's why your output voltage here cannot occupy too much voltage. Therefore, the gain is very, very small. It should be very, very small. Say you're ending up with a gain with 10 ohms load here for the first stage C. Your gain, it turned out to be like 1 or even 2 or even higher. Definitely something wrong. That's impossible. What gain you got?
I think
Yeah.
I tried the without the load, the gain was as I had calculated essentially.
Mhm.
But with it, it was like I think I want to say it was point like 2 or something, but that was with a capacitor. So that's what I was wondering.
0.2 is a good gain. 0.2 is very good, actually. 0.2 is very good. And also be careful when you read the multisim. Okay, read it correctly. Yeah, if any questions, you can shoot me email, or we can make an appointment to talk on one-on-one basis. Otherwise, just good luck with your exam. Okay, Thursday, 1 o'clock. Okay, 1 o'clock in the 90 minutes. All right, bye now.